Okay, Raven is with me, and Raven, you agree to be recorded, right? We're going to be recording this.
Absolutely.
All right. Now, Raven is interested in nuclear physics and fusion. Everybody's really big in this fusion thing. Now, before I get started, my interpretation of fusion is completely different than mainstream interpretation of fusion. There's two completely different species, basically, of the same interaction. Mine is subnuclear. Theirs is nuclear. It's atomic. Now, yes. they're breaking up big things and then creating heavier things, and part of what's fused together is dispersed as energy. But it takes more energy to break that apart, and they're only getting blasts of energy, and they're trying to make it into a huge infrastructure oriented device that's very vulnerable and very complicated and very expensive. Now, my interpretation is this yellow little box right there having our photo-optic chip, which would be a laser and a receiver at the same time, focusing to a venturion. I'm going to show this in pretty good detail in a minute, Raven. But let me just show you what they said on 60 Minutes, because everybody's talking about fusion. And it's just a fusion. And I heard Neil Tyson and a guy called Chuck Nice. He's been doing videos. Huh?
I heard that one as well.
Yeah. He's been doing videos with Chuck, apparently, as in the Star Talk. Now, I'm hoping that we can talk together, and if we can, I want to show you what I think we can actually accomplish and get free energy very, very quickly. Now, let me just show you what they have to say. Everybody's talking about it, but it's 10 years away at best. Listen. Okay, my friends, this is 60 Minutes. Most people know what 60 Minutes is. A very good news program. They have a lot of interesting things on. He's talking about, on the last minute of the broadcast, about fusion and how important it is. However, fusion that they're talking about is on an industrial scale, very complicated, very expensive, grid-oriented, very vulnerable. I'm talking about walking around, something like this, where you could just walk around with it like a lunchbox. And you could walk in the woods, you plug anything into it, just like you're plugging into this stuff now. USB, 120, 220, European, whatever you want. Now, here's what he's got to say, and he's right. Listen to what they say.
Energy, the same process the sun uses to create heat and light, promises to be clean, cheap, and nearly unexpendable. It produces neither greenhouse gases nor nuclear waste. The breakthrough's practical applications are years, even decades away. But in this season of hope, it sheds a little light in the darkness.
Okay.
I'm Bill Whitaker.
That's Bill Whitaker, and happy Merry Christmas to you, my friend. And yes, it does shed a little bit of light, but we need to look at photonic fusion, not nuclear fusion. It's two different species, totally. All right, let's get into that, because they are two different things. Nuclear fusion is, hold on a second. I think I did, well, let's just look at the videos. Okay, I think this is going to be kind of fun. It really will be. All right, I'm going to just explain to you. This is the guy I just talked about, Chuck Nice.
Yes.
Now, he was talking with Neil Tyson, and he seems to be very, very interested. He sounds like a good humanitarian. And he's looking to see what he can do to help the Earth, to help the global warming. That's what his statements were. Now, I just go on about my mud fossils and so forth. But anyway, let's go to the next little clip here. Okay, my friends, huge. Oh, okay, this is huge. Can you read this? Radiation hard monolithic CMOS sensors.
I cannot read it from my screen, but
okay. Well, it's going to be what it is. Let me see if I can find the article about it.
And folks that listen to me and folks that listen to Roger, please note that we haven't rehearsed this. We're just actually having a conversation for you all. So I want you all to know that.
Yeah, this isn't anything set up. It's a Roger ramble. That's what I call them. Now, anyway, let me come out to where it make a little more sense out here. All right, let me see if I can explain what happened here. Rod Warren posted some pictures of light, which just blew me away because I could realize what was happening based on my understanding of the dipole nature. All right, light is a dipole. Let me probably best to show the pictures. What do you think?
Yeah, absolutely.
All right, let's
go.
go.
The interesting thing to me is like they're always trying to go heavy and industrial and huge, and they're using all these heavy metals and all these metals that will contaminate anything, and they're very hard to control. I mean, Fukushima's absolute proof of that. When I have watched you do this with a light and demonstrate how it works, and I think people need to know this because there are more than one way. There's more than one way to create fusion. It doesn't have to be industrial, and it doesn't have to be as dangerous as they're trying to make it.
Right, I 100% agree. We use light. Now, if you see right here, this Fermilab particle up here, the black one and the red one.
Yes.
They used head-on collision of protons. In my world, a proton is absolutely gigantic compared to light. We're using light. You see down here, this is light.
Yep.
Now, what they did find, though, was the exact same particles we found. This black one and the red one. We found exact same particles, only we found them in light. They found them in debris, like literally trash, in their particle smasher. Because they were hitting things that are literally thousands and thousands of times bigger than ours, and then they just see them, they say, wow, this is the smallest particles we could find. And what they did was they see this big black one, and they say, that's a heavy particle. It's just a fixed particle. That's what Fermilab says. They call it a fixed particle. It means it never loses mass, and it just is, that's the smallest particle you can have, and it's heavy as hell. The white one, or the glowy one, is almost no mass at all. And I agree with that 100%. Because when you watch the atomic bomb explosion, you saw that, right?
Oh, yeah.
All the house does is just burns, and not even the actual curtains inside the house just barely move, and they just burn up. And you saw that. I mean, it blows your mind, because all that's hitting it is this glowy one, but it's got nothing more than burn to it. No movement to that curtain virtually at all. Do you agree?
Yeah. If you don't know what we're talking about the nuke test that they did in Nevada. Exactly.
Yeah.
Excuse me, y'all. But now, could you go back and explain I've seen you do this before, but when you have that separation between the black particles and the light particles, can you explain to people how that process works?
How the separation of them works?
Yes.
Yeah, well, here, let me show you here the nuclear bomb blast. And this will make it quite evident.
Ready to start eating healthier?
I think.
Meet Kachava.
Never fails, right?
Yeah, well, everybody's got to make a living. Now, here's what happens here. I'm going to show you, this is, I'm going to turn the hold on. Whoops, here we go, here on. All right. Let me come out to I got a house here that goes up really nice so we can see it burn up good. This is the one right here. All right, here goes. Now, this is Atom Central. And this house is going to be hit by nuclear explosion. I got it on hold right now. Now, here's what I'm going to explain to you. Everything that's combustible out here, all the shingles and so forth, they're just going to burn. There will not be any movement whatsoever of the house, because the first thing to hit it is the white particles.
Yes.
And the white particles surround the dark particles. We never knew this. Nobody's ever seen the dark particles because they're always surrounded by the ones that we can see, the glowy ones.
Yeah.
You understand,
yeah,
right?
Folks, to explain what he's telling you is what we see is we perceive it as the fire or the radiation coming out from the explosion. Those are the light particles that we're seeing. We're not seeing the dark particles that are within that explosion. All right?
Right, exactly. You don't see them, but they follow the white particles so quickly that you miss it. Now, I have this on very extremely slow motion. Now, watch what happens. The house will burn. Remember this. Look up here at all of the wiring and everything. The only thing that doesn't burn is the metal cylinders here on the side. And the reason they don't burn is because they're able to absorb the electrons in such a way that they're not combustible. Let's just put it that way. All right, here goes. Listen, watch what happens. I got the sound off, and the first thing you'll see is just blistering whiteness. All right, so here it goes. It's bam. All right, I stopped it. That's all you have now is electrons there. Now, you see no movement whatsoever. I'm going to let it play now. And again, it's very, very slow. Now look at what happens. It's just burning. It didn't go anywhere. You see it? I'm stopping it. But you can see what's happening. There's just no combustion. I mean, there's no,
Yeah, there's no motion.
There's
instant heat.
Just nothing more than atomic invasion of the electron particle, which has no mass. Now, watch what happens when the black particles come, because they will be following the white. Because the white, remember, always, 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 always surrounds the black. The black will be in the center. We never knew this. We never realized it. But the Russians proved this in space. And I'll show that in a minute. Watch this. Here comes the black. Here it comes. Get ready. Boom. Now watch what happens to all of the dust and everything. It turns around and comes back. You see it turn around and come back? It's coming back to fill the void. And also...
it creates a vacuum.
Yeah, right. And it also, I believe, the dark matter, because it's gravity. The dark matter is gravity. So the dark matter... Here, let's go down inside the house. Watch this. This is inside the house. Let me play it and see. Watch that. Look, that's all that happens. And then watch. Boom! It's all over. You don't want to be in that house.
Well, something else to point out there too, Roger. If you look at the louvers on the window blind, them things turned black and were burnt before the pressure wave hit.
Oh, absolutely. That's the whole point of it. There is all that white particle has no mass whatsoever. Watch. All it has, here goes. Again, very slow motion.
Folks, watch the louvers.
Yeah. Get ready. All right, now I just stopped it. This is the initial invasion of the electrons. All right, these are the electron neutrinos, the white glowy part of the particles I showed you. Now, and again, very, very way down slow motion. Here it comes in a little faster. Here it comes. Boom. You see it? There's a tiny, tiny, tiny puff of smoke. See it?
Yep.
So there is some tiny compression. And I'll show you what they say at Fermilab, and I have to agree with them. You see that? There's something there.
Look at them louvers. Not only have the louvers been burnt, but it's burnt the wire. It's burnt the strings in them.
Exactly.
So that shows you that the heat was delivered before the pressure wave.
Right, but you did see that there was the tiniest bit of concussion. Watch again, real careful. You see that just a tiny pop. Watch. This is important because this is really exactly identical. And see it pop up just a little tiny bit?
Yep.
Now watch it careful. You see it come out? You see the smoke come out here?
Yep.
There's pressure there. There's pressure. You cannot deny that. There is some form of pressure there. And you see it pop out, but nothing like you would expect from a nuclear bomb. And,
absolutely. I think that's a very, very, very important reason for us having this conversation, because what you're talking about is exactly what we've just watched. First, you see the electrons hit, and then you see the black particles hit, which is actually your force.
Exactly. So that shows us that there is two bits to the nuclear bomb. The first one is the white particle has no mass. Now let's see what Fermilab has to say, because I could tell you right now it's exactly what they have to say. I mean, identical, word for word. Whoops, this is well, here's the two particles, the black and the white, the Dirac, they call them Dirac neutrinos. All right, now let me find, hold on. All right, here it is right here. This is what's the point, Don Lincoln. These are the two particles. Here's what he says about them. Let's just cut right down to the chase. He says, in summary, the extended particles, which is the black one, have a fixed size. They never change. They may have a fuzzy edge, which is that, is that red little glowy edge.
Mm-hmm.
The point-like particles are mathematical abstractions with zero size, those red glowy ones.
Mm-hmm.
It says even zero-size particles have an extended effect due to the effect of the field surrounding them. Yes, I agree with exactly.
Absolutely.
That's exactly what we found. Now, they also claim that the quantum foam is exactly what I say it is. Empty space is not empty. Empty space isn't empty. It's not. It's covered with, where do you think the light particles come from? It's amazing they don't.
They don't make the connection.
It's unbelievable. And then the last thing Don says is the Standard Model is the most successful theory ever. It is not. It's not successful at all.
No, it's actually a bad theory.
Well, here's the problem. They have seen all of these particles. However, the W and the Z boson are the only two particles that exist, and everything else is made of those two particles. Everything.
Mm-hmm.
And I can show you that for a fact. Because
it's interesting to me, Roger, that they have been so locked onto this macro fusion and macro atomics rather than looking at the subparticles and what you could be doing with those more safely.
There's no money in it.
Well, you do have a point there.
That's exactly what it is. What I'm showing right here, we did for less than $500. You see this right here? That's fission and fusion.
Nice.
Over here is where the black balls separated from the white. You saw them together. They call gluons. I'm going to show you the atomic structure in a second.
Well, do me a favor and explain to folks exactly how this separation, this process was done.
Here, I'll show you the whole shooting match. Hold on.
Well, I know that you've done this before in your videos. I've watched them, but it's very important for people to see the process.
Yeah, I agree. I just got to get back to the, I got so much stuff in here, man. It's just way out of control.
Folks, I would do a conversation with Roger even if we weren't recording it, because I just enjoy the opportunity to pick his brain and have a conversation with someone who understands what I talk about.
Well, I just, it's funny because I just popped in this morning and somebody sent me Michael Tellinger talking about atomic physics. And I had you know who Michael is, Michael Tellinger?
Oh, yes.
Yeah,
yes.
Okay. I did a Zoom with him. We spent, a couple hours at least.
Nice.
Yeah, doing the same stuff we're doing now. But anyway, here, and he was. I'm going to be doing a lot, hopefully a lot with Michael about everything.
I like Michael Tellinger.
Yeah, he does everything. He does the same stuff I do, and he's fortunate enough. Basically, I believe he basically works for himself, and that puts him out of the realm of being vulnerable. He can talk.
Exactly.
Anyway, here's how this happens. Let's go to the top left panel here. You can see this well?
Yeah.
All right. Here's the pulsed red laser. You see this pop, 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 pop? That is a pulsed red laser. All that is a construction laser sending out pulses to say how far away is something. Now, you see the tip is the leading part of the wave. The wave is a magnetic field. That's all it is. It's a field. There is no particle there. The particle is way back behind the wave. The wave is pushing its fields against all the other fields that are in the air. You see all the other little red glowy spots all over the place? Those are being shoved.
Yes.
All right, so you have a push. I call it push to shove. Somebody's coming through pushing everybody out of the way, and the other guy shoves back. Now, the guy that pushes, which is this guy, is usually much stronger than the guy that shoves back because they just push right through him, but they both glow. Now, so the wave is beginning to accelerate now, and the reason is acceleration is because of this Venturi, which is right here. Now, a Venturi is a crusher. You can't see it because it's on steroids glowing. But what it does is it forces all these particles on that angle. You see the angle here and the angle here? It's forcing all those particles to congeal in the center. And then there's a slit that's so tiny that only the white can get through. Because the white...
basically it's creating a pinch point right there at the point of contact.
It's a pinch. Exactly. And that pinch says only you white guys can get through here. The black guys are fixed, remember, don't forget, they're fixed and hard. They're slammers, they can't get through. The glowy white ones, there's no mass to them, they just squirt right through there. Now, why do they spray out of here like so violently when we saw them go into that house and hardly even move the blinds?
Yes.
The reason is the black is pulsating. So we're going bam, 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 and it's squirting the white through here violently.
So what's happening is the black particles that have a constant mass are actually being, it's like using a jackhammer, basically.
Exactly.
They are the ones that are actually causing the pressure because they can't get through.
They are also called the carriers. Light doesn't, apparently that white thing never goes anywhere by itself. It has to go with a carrier, the black particle.
It has to have something with mass in order to convey it.
Exactly. Now, it's ahead of those black particles. We saw that, but there was virtually no concussion to speak of whatsoever. So they're really just sort of a field surrounding the black. And I can show that. Where do you see this? This is going to blow your mind. Watch this. Coming out of this Venturi is this glowy spot right here. You can see this. Then it attaches right here into these Higgs fields. Well, why does it make Higgs fields right here? The white has to get back to the black. Right there, it starts to reattach.
That is the back wave. That is the back wave that we saw in the nuclear explosion.
Where do you see this? Wait till you see this, my brother. This is exactly what happens. You saw the Higgs fields. You see this?
Yes.
These were the Higgs fields. At this point, they're just white. There's no black to them at all. You see up here at the top, the real white looking stuff?
Yes.
Down here, they're starting to become black again. You see the black being surrounded by the white?
Yes.
That's the tip of these fields. And that's a picture of it. That's no artist rendition.
So it's created like a vortex in the passage through that Z point, or that pinch point.
It's right now, what's happening in my estimation is the tips of these waves are now the white part. You see back here in the back part of the wave, these are like cones. The tip is here. Let me, well, I can show you better pictures of it, but you can see the tip is like a cone. So the back part here is still very white and not attached to any black parts. The tip of the front is starting to attach to the black. Reattach, because they were white. They were just 100% white a second ago. So they have to come back to the black.
So now the question that I have is if the black ones are being constricted at the pinch point, are the white particles connecting to new black material?
I would believe so. I can't see those black balls jumping ahead of them. Absolutely not. No way. There's got to be excess black particles. And I also believe this is gravity. The black is no question is gravity. The white pulls back to it like unbelievable. And the white is the black is the gravity. Let me show you, see something.
So you could actually harvest energy at both points. You could harvest energy at the Z point where the pressure is the highest, and you could actually harvest energy on the backflow where they're trying to reconnect.
Well, my feeling is that the best strategy would be to spray these particles, only the white, which is the burny part. Only the white is coming through there. You understand, right?
So you'd harvest the hot particle.
Exactly.
Energy.
You just go for the hot
Gotcha.
ones. You just take the hot ones because they're not even pushing. There's no damage here. You're not even exploding anything. All you're doing is absorbing these white glowy particles. At this point right here, as far as I'm concerned, this is
you would not have to deal with the compression from the pressure of what we normally see as a fusion reaction.
Exactly. You're going to have something going on up here, but it's not. Rod did this for 5 years in his house with never having any issue with himself. And he used the same phone. This was just a cell phone. Now, this was just, and he's still using it now. And it was
what about heat generation?
Doesn't seem to have any heat generation at all because it's coming right back to itself. Now, they're talking about exactly that at CERN. Here's what they're just talking about at CERN. Let me show you something. Where was it? They're hardening their...
Yes, CERN had to harden their system because of the amount of pressure that they were creating with the force that they're using.
Here, hold on a second. We saw enough bombs going off here. Hold on, let's see.
Now, I think another thing to point out to folks is the system that you're using is just light driven. It's a pulsing laser.
Here,
there's no 3-mile magnet driving these particles. It's just a pulsing laser, and that's a huge difference too as far as infrastructure and cost.
Listen to this now. I was just reading up on this article today. Now, this is from CERN. This is CERN. They're high luminosity. Large Hadron Collider. Luminosity means glow. If you didn't see glow in the particles I showed you, then you got to go to the eye doctor.
Yeah.
Now listen. Here's what they did. I don't want to brag, but if it's true, it's true, and it's true. In 2015, I did a video called "Light is Dark Energy and Dark Matter in the Vacuum of Space." And it is. because it contains these particles. And I contacted CERN and Fermilab and everybody, 100% of them. And they all said, you're crazy, you can't see these things. And I said, no, you can see them with CMOS. You see up here CMOS sensors?
Yeah.
I said, we're using smartphones, we can see them. And they said, no, you can't. I said, yes, we can. And I said, and as a matter of fact, I am showing you, and this was with Don Lincoln, I said, and this was Don Lincoln, I said, this is 2013, this was around 2015. I said, I'm showing you the particles you found. And he said, no, you can't see. We really had it out, back and forth, many, many times. And finally, he said, just don't ever call me again, don't contact me. So that's how it ended. But I said, I see your particles. Now, listen to this. Now, they're the one touting the CMOS. It says, but they want to have radiation-hard monolithic CMOS sensors. Well, if you're hitting head-on protons, that's different than squirting out light. We get hit by light all day long, every day. Now, can we take that little bit and piece very short, quickly, and put it into a container so that we can use it for running engines and anything like that, like into a battery, or make our cars run, or heat our houses?
We use light all the time with solar panels, but solar panels are not as efficient as people like to believe.
No, they're not. They're running now about 22, but this new stuff called perovskites, and they're nothing more than CMOS. It's all it is complementary metal oxide silicates. They take a substrate, a base, and then they layer it with complementary metals and oxides. And what will happen is when you shine light on it, it's literally like a guitar string. And you absorb those frequencies. And they turn them into, we could turn them into particles. And that's what they're doing.
Well, now this is what I've been working on, Roger. I've been working on the opposite. I've been working on using sound for energy. Could we not take this force and convert it into a frequency, as just like you said, a guitar string, and use that for your energy?
Yeah, but how much energy are you going to get? Everything is push to shove. The harder you push something, the more energetic value you're going to get. And I don't see anything never seen anything as energetic as that first wave of light from the atomic bomb. That is just 100% energy. So that's where you want to go. Now, yes, just like Nikola Tesla said, hold on, here it is right here. Here's Michael.
Well, see, that's the reason why we have been working. That's the reason why we have been working with sound, because you take sound and convert it through a magnet.
Go ahead, say it again.
I was going to say, is we have been working on the opposite solution. We've been working on sound and using electromagnets to try to solve a energy issue. Converting sound to energy. We do it all the time when we play music on our stereos, right?
Yeah. Everything isn't. Listen to this. It's funny you say this, because I was just looking at Michael's video this morning. He's talking about Nikola Tesla.
All right.
God lives here. The full explanation. Now this is Michael, and it's funny. All of this stuff falls into place, because I was going to do a video today about what is life all about. What is the purpose of life? Do you think it has a purpose?
I would hope so. I always have thought.
Well, there's a lot of people that don't have. Literally nobody I know ever considers any of that stuff. They just don't even think about it.
I think everyone has a purpose. You just have to find what it is.
Well, I see almost everybody's purpose is self-interest. And
unfortunately.
Well, I understand that to a degree, but once you become self-satisfied or satisfied with what you have, which it doesn't have to be a whole lot. You're a Native American, a Cherokee, right?
Yeah. Well, Roger, for me, it's once you get to the point where you have your needs met, and you are able to give time to other things, like these podcasts that I do. I think at some point in time, if you do not get yourself to the point where you become service to other people, then you are not fulfilling your purpose.
Yeah, exactly. I had another indigenous person. I can't remember where they were from. It's amazing the people that are contacting me from all over the world. But this guy was another tribal type person, and said that in his culture, anything that you do not need is poison.
Yes.
Can you imagine? Well, it is. I got so much crap around me that I can't stand it anymore. I just want to throw it away. It's just junk.
The old saying is when, at some point in time, your possessions come to possess you.
Yeah, I don't want any of it anymore. All I want to do is try to figure out what's next. And I'm telling you right now, my friend, there is no question whatsoever in my mind anymore that there is something's going to happen. Now, and it can be good and bad. Before, most of the people I know think, I'm just a nice person, everything's going to be good. Well, that might be true. But I think you're supposed to look and think a little more than just hope for the best. But anyway, listen to this. This is funny because here's Michael this morning. Here, listen to this. This is fabulous. He's pretty good. He's entertaining too. He's got a nice way of talking. And by the way, here's how I got hooked up with Michael. About 4 or 5 years ago, he found a rock, and somebody said, "Boy, that looks like a heart." And he had a doctor, a heart doctor, on his tour, and the doctor said, "Yeah, that is a heart." So he gets a hold of me. He says, "I found a rock that's a heart," and he says, "I hear you are a mud fossil guy." And I said, "Oh yeah." So we went back and forth several times, and anyway, that's how it started. And
folks, I gotta. If you folks that listen to me and folks that listen to Roger have never paid any attention to Michael Tellinger, he is someone who has been at this for a long, long time.
Yes, he has, and he's got those stone circles in he's over there in South Africa, and he's studied these stone circles. Very, very strange, and that's my realm is stone. So anyway, let me show you this.
A lot of energy.
Well, every stone is a body part. I'm telling you, 100%, no question whatsoever. 100%. Oh, by the way, listen to this. Before we talk about Michael and God lives here, I've been posting about everything in space being biological. Right? You've seen those.
Mm-hmm.
All right. Now,
yeah, have you seen that? Have you seen the images of that new? Have you seen the images of that new asteroid that they've seen that looks like an embryo?
Not really.
I wish I could tell you the number of it. I'll send you a link, but to the video. But there is literally they have found an asteroid and they have figured out a way to map it, and it looks like a embryo about. I don't know, maybe 7 or 8 weeks along.
Well, let me tell you something. Jupiter is about ready to give birth.
Yeah, so I looked at that. I looked at that closer.
Yeah.
It's definitely, and I rewatched your video footage instead of listening to my audio, and the changes. If people could not see that there is something going on there. I feel bad for him.
No, yeah, it really is tragic that people can just miss this and it doesn't matter. But anyway, listen to Michael here. Watch this.
No matter how I look at it, how much...
Hold on, let me tell you. Michael, you're too loud. You're coming on too loud, brother. Hold on a second.
No matter how I look at it, how much research I do, I keep coming back to one guy that stands head and shoulders above all other researchers and inventors of, I don't know, for how many centuries. And that guy's name is Nikola Tesla. He says if you want to find out the secrets of the universe, think in terms of energy, frequency, and vibration. That's exactly what I've been sharing with you here.
Everything we've been told is a lie.
Everything in creation spins and vibrates. Everything has...
All right, here's what you were just talking about, is frequency and vibration. Yep. Now, we are in, if you're way down in the radio and the microwave, infrared, down there, that's basically sound. If you just keep going down below, lower and lower, it's just sound. It's and it's just a very, very slow wave until you get up to where it breaks through the atmosphere. Otherwise, you get sort of a pushy, bouncy wave. And then at a certain point, it starts shaking molecules. You're sort of shaking fabric. That's the best way I can.
Well, it's how we hear. It starts to vibrate enough that the molecules start moving, and that sets off the vibrations in our tympanics.
Right, and it's exactly. Basically, it's shaking a fabric sheet.
Mm-hmm.
All right. Now, if you were hit that with microwave, you're going to either burn a hole through it, or you're not going to hear it. And the same thing with infrared and visible. You're not going to. It's going to be a whole different thing. So we're way down below the radio frequency. Radio goes through the airwaves and so forth. Anyway, gamma radiation is like almost touching particles. They're just right through the air. Now, I could show you all this stuff in our light, because we did all of that.
Yeah, gamma vibrates at such a high frequency that it actually causes cellular damage.
Yes. But you also have to be, hold on one second, let me see. Yeah, gamma, you can focus and create a spot of intensity.
Mm-hmm.
And that's basically what I think they do with the gamma and so forth. We're doing, boy, I wish I could get this thing to home in for me.
Like I said, folks, we're having a conversation, and you just happen to be able to join us, which is really nice.
This is what research is all about. It's time consuming.
Well, and the other thing too, folks, is a lot of people don't have time to just sit down and converse. And unfortunately, that means that a lot of things that we can relate to each other, and it may be some really obscure thing that we talk about that creates new ideas or new ways of looking at things. And that's what's missing from the academic and the industrial energy industries, is that they're so concentrated and concreted into their box of thought that they won't listen to people like Roger or me or Tellinger saying, hey, look, have you looked at this? Well, no, that won't work because we've never done it that way. That's the problem that we've been running into for 50 years.
Well, what we need is somebody outside the system, because the problem is the system feeds on itself. Once they have, their infrastructure is literally, and I'm not kidding you, trillions of dollars. And their annual budgets are billions and billions of dollars. They just did an upgrade to do exactly what I told them. I said, you have to focus, and you have to use the CMOS. And this is right here. You see this? This is focus, baby. You see that?
Nice.
That is all 100% white. 100%. Well, you could see a black particle here and there, but almost 100% white. And then these Higgs fields are as they begin to attach to the black particles.
Mm-hmm.
And there is so many particles, it's just unbelievable. But that's exactly what they say. It's an electron shower.
Now, you said that you've actually had this system, the gentleman that's working with the light for you. This has actually been running for 5 years, and nothing's.
7 years.
He's not had any issues. 7 years.
7 years. I mean, he hasn't had it running continuously. We did this experiment. Here's what happened. Rodney Warren from Australia was posting all kinds of crazy looking pictures of light. And, you know, it started to look kind of silly after a while because nobody could understand what he was doing. And I understood immediately. And I got a hold of him. I said, Rod, how did you do this? And he said, well, I was doing a double slit experiment, but using a single slit.
Mm-hmm.
And I said, no, something's not right here. That's not going to produce this result. I said, explain precisely what you were doing.
Mm-hmm.
And so he's not a real corresponding guy. He doesn't talk much at all. So anyway, I drilled it out of him that he had put 2 nails, literally nails, side by side into a piece of wood, and then put his laser in front of it and shot the laser into the nails, which are circular, which created a venturi, which is a pinch point.
Yes.
All right. So all he did was create a venturi. Now, I just did a video on how to do this, how to make, and we should watch that because I can show you how to make one of these. And then we put the harvester right here. It's nothing but right there is. I'm sorry. Go ahead.
You would have to collect the energy right beyond the pinch point.
Exactly.
Folks, to explain to you in the macro, and I'm sure Roger has seen this, and if not, then it might be something new to him. But when you look at what they call the Birkeland currents that flow through the galaxy and flow, you can actually see them out in the universe. They look like synapses in your brain firing. And at the points where you see solar systems, the star at that solar system is a pinch point of energy. And you can see these, excuse me, you can see these in imagery at different frequencies or different spectrum, let me say it correctly. And at that point of the Z pinch, or the pinch point, is where the energy is focused at. That's the reason why the stars work the way they do. And you also see it at the center of galaxies, the pinch points. And it creates these energy waves. At the macro now, I'm talking about in extremely large scale. What Roger is showing you here is that Z point, that pinch point that Tesla was talking about with his energy. And if you look at the structures that Tesla created, he basically created this pinch point at the base of his collectors. Now, was he collecting this energy? Was he collecting electricity that was floating in the air? I couldn't tell you. I'm working on that. But that pinch point right there is exactly how Tesla was collecting his energy and using it. It's exactly how your stars collect the energy and use it. They create this pinch point, and that's where that energy is coming from. I focus in on the electric model of the universe, but it's still fusion. It's just fusion using electromagnetics and light.
Really, basically what you want to consider, it's crushing particles against other particles. That's all it is. And what we did, we forced them to come side to side, which is no difference whatsoever than hitting them head on, as long as they can't get away from each other. As long as here's the problem with CERN and Fermilab, is they're going around a circle one way and around a circle another way, pumping them up until they have high energies, and then trying to force them to hit head on. They will not hit head on. They will not do it. There's a rule. It's called Kirchhoff. No, not Kirchhoff's. I forget what it is, but it's when two fields hit head on, one slides off the other. It's just the way it works. And so we're forcing them not to be able to get away from each other. That's why we're so. This is just beyond perfect. Now, and when they come out of here, look at the particles reattaching. You see all the black reattaching to the white?
Yeah.
That's what an
outside of the bell, it's starting to reattach. Yes.
Right. This is when they're coming back together, and that's where I showed you those black particles are reattaching to the white ones. This is where the Higgs fields start to come. If you're sitting right in here, you're in that blind zone, right just before those blinds.
So basically what they're seeing in the Higgs fields is after the energy has been focused.
Yeah, after the energy has been smashed into. A Higgs field, they got it just backwards. They got it totally backwards. They think the particles come out of the Higgs fields. No, the particles come back together into Higgs fields.
There you go. There you go.
I can show this too.
Well, you know, and the other thing too, the amount of energy and the amount of force that they're creating at CERN requires all that heavy equipment and containment. Well, you know, they couldn't get their grants if they didn't have to build those big machines.
Here's the problem. Here's the problem right here. There's the Higgs boson. For them, everything emanates from the Higgs. It is not that way. The only particles that exist, the only two, is the W, which is the white one, and the Z, which is the black one. That's all that exists. If you put a W and a Z together, they're glued together, it's called a gluon. That's all that is, the W and Z together. We know it as an electron, because an electron has the dark side. We never knew that. We never knew it. It's a dipole. We always thought it was just a negative. It is not. Now, you take the two gluons, which are both dipoles. You take each gluon is a dipole, like a little dipole magnet. You put two back to back, and you have your photon. That's all that exists. Now, if you break apart the natural gluon, because gluons is the natural. If you're in the electronic range where you have lightning, static, electricity, heat actually is gluons. Photons are a little different than heat and electricity and static and lightning, which always will seek ground. It will always seek ground. Why? Why does it seek ground?
Because it's already separated. The charge has been separated.
Well, the black part is dark matter, and dark matter is ground. I can show you that as well. Here it is right here.
So what's happening with a lightning bolt or that kind of a structure or static is we have somehow created enough friction or separated those particles, and they are trying to seek balance. So like when you reach out to your doorknob and ground yourself, you're actually bringing those particles back together.
You're actually bringing, well, here's what you're doing. You're bringing those particles down to Earth. Here's what happened. This is the Russians in space. And they took a vacuum chamber. So they sucked all the particles out of there. And then and this is in zero gravity, so there's nobody, it's not flattening out. That's the key. Now, the nature of a charged particle is to go to the center and make itself black. They injected this with charged particles, which they had expected them to all separate from each other like a bunch of boxes, and each one of them separated by its own field. And they saw this thing, a big black hole in the center, and they freaked out. Now, this is our Earth. Our Earth is nothing more than dark matter inside our Earth. Now, I think our Earth could very, very, very well be hollow and filled with this dark matter. Because you see these white particles? They will eventually congeal almost exclusively and make a nice tight seal around this dark matter. And the reason is, it is gravity. And that dark matter is that black ball that breaks away from the other ball, the glowy ball. And so their nature is to be separated. That is their nature. The only reason you see them flat against each other, and they point that out in this video, is that on Earth, the gravity makes everything drop to the bottom, so you have a complete white line here, and the gravity is down below the black. And that's what creates... That's what
that would fit with what they describe as the firmament, wouldn't it?
Well, the firmament is the ionosphere. Here's what the firmament is. Let me show you what. Everybody gets confused about this. The firmament.
Well, what I was saying though is that separation with the gravity pulling the dark in and leaving the white around the outside.
It is, yes.
Would that not be a very adequate, at the micro scale, description of what our firmament would be?
Yes, but yes, it is. The firmament is actually sort of firm. And what it is, let me see if I can. Boy, I'll tell you, I got to get this thing.
I bring that up because a lot of times we look at only the things in the macro, the large scale, and we ignore the micro scale that actually creates it.
Hold on, let me see if I can get my light. Here we go. Now we got something. Now, where was I going with this? Oh, I want to show you something about outer space. You were talking about the vibrations in outer space. You want to see something? This is Rod's nephew, Dylan. Where do you see this? I showed you the black hole. Now this is Dylan with his new phone. He took this picture. Those are all magnetic fields, and you can see all these things in space are dipoles.
Nice.
You see that?
Yeah.
This is something it almost unbelievable. This is a double field particle. Well, not particle. It's a planet. Now, explain this to me. You see this field here, this one tight, it's down here?
Mm-hmm.
And then you see this one here like a little behind it almost?
Yeah.
It's got two fields in one particle, in one planet.
Uh-huh.
And the dark and the white have sort of a strange pattern to them. Here's what's going on. I believe this is Venus. Venus spins backwards and forwards.
Well, and please notice that is a toroid.
Oh yeah, wait till you see the rest of the stuff. This is going to knock your socks off. Now, I've been watching this stuff a couple of years now, trying to figure this out, and I think I got it pretty well figured out now.
Roger, when you get the chance, can you send me that image?
Yeah, I got some more. I'll show you some more. Now, watch this. You see how tight it is down here at the bottom, these little push-to-shoves? That's what all this is. Blah, 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 blah. That's the frequencies that Velikovsky's talking about. This is energy, very energetic at the bottom and very less energetic at the top. Now, the Venus spins backwards on its axis, and it spins forward around the solar system like we do. We have a magnetic field, but it's only one magnetic field, not two. They have one that's created by the spin around the sun, and another one by the reverse spin of the planet. Can you imagine? I'm not kidding you. That's the only way you can get this. That's the only way you can get this.
Well, yeah, what he's talking about, folks, is even though Venus travels the right direction, like the rest of the planets, its rotation is backwards.
Check this out.
Wow. Look at that.
Woo-hoo.
It almost looks cometary, doesn't it?
It looks like a looks like a pyramid up there.
Wow.
No, I understand this. I've been studying this for well over a year.
Well, and what I find most interesting is that actually demonstrates the toroidal effect of the energy around that planet. It actually shows it.
Well, yes, but here's the key. The only way you get these fields is because there's a ball of particles that surround the planet, and the planet spins just like a motor. A motor is an electric motor becomes a generator if you spin it by hand.
Yep.
All right. The planets create a magnetic field. because they are spinning because they're scrubbing through space. So as they spin, they create a field, and I can prove that with this picture right here. What are you looking at, that yellow thing? What do you think that is?
It almost looks like it's generating an energy.
This is the moon. This is the yellow thing is our moon. Now, you don't see a magnetic field around that moon, do you?
No.
There's no magnetic field around our moon. But you do see blue on one end and yellow on the other. Why?
Is that where it's breaking through our field?
What's happening with our moon?
It's kind of like a shock wave.
Yes, it is. Precisely. That's a very good way of putting it. It is a shock wave where we see in the blue. Blue means you are increasing the energetic value of what you're seeing here.
Mm-hmm.
The yellow and the reds are a decrease in the value of the energy. So there's almost no question whatsoever. The moon is moving this direction, straight up, and it's impacting here, causing the blue glow, but it's not spinning around.
What you have is you have the prow of a ship breaking the wave, and then behind it you have the outgoing wave.
Right, but there's no magnetic field. What you're seeing, this field here, is created by some other, I don't know what it is, but it's behind the moon.
Could it be compressing our field as it moves?
Well, yeah, it does, because the tides show that does that, and the seasons and all that. It depends on how close and how far away we are from the sun, and the angle of the axis of the moon, of the Earth, and how how effective.
And also the moon does not. People think the moon is always in the same, but it's actually, if you watch it over time, there's actually a figure 8 that it creates, and that could be the compression. See, it's like a compression wave when you're running a boat through water. So that would actually be a visual cue as to why it creates the tides the way that it does. It's actually affecting our magnetic. it's affecting our magnetic field the same way that a ship affects water when it goes through it. That is an amazing photo, Roger. I would love it if you could send those two to me. I've got a friend that we've been talking about this, and that actually displays exactly what we've been talking about. Thank you.
Yeah, sure, no problem. I share any of my stuff, and I use anybody else's stuff. So now let me show you something,
folks. This is why it's so important for folks to talk. Like Roger with Michael and me with Roger, and I'm going to share this with other folks that I'm working with. And the reason why is because this is how science is supposed to be done. It's the way it used to be done.
Yeah, everybody wants to protect and copyright. I got thrown off of Facebook because I was showing stuff that was copyrighted, and they said, no, you're done, and they didn't even give me a chance. They said, it's over, case closed, don't ever come back, and they won't let me back. But anyway, and plus I have every single right and legally to show anything I want, copyrighted or not, without any permission from anybody, because I am doing it for transformative educational purposes. Now, let me just show you this. You see this little...
And you know what really makes me angry about that, Roger, is when someone or a group of people are working contradictory to what the industrial complex is doing, they will go after you with hammers and nails and sledgehammers to get you taken off or deleted or blocked or whatever. Because sharing, folks, you got to understand, yes, the industrial complexes, whether it be energy or whatever, are doing good work. But when we take their work and we start adapting it to the things that we're seeing, they don't like that because we're cutting into their profit margins.
Yeah, well, everybody is like I say, self-interest is the rule now. But anyway, let me show you this. Here you see this one over here? You see my cursor going around, right? That is Venus. Yep. That's Venus. Mm-hmm. Look at that field. Look at that field.
Wow.
It's white and black in the center. Not supposed to be that way whatsoever. It's white on this side and black on that side. Not supposed to be that way whatsoever.
Mm-hmm.
It's because it's spinning backwards.
Well, and you can see the bow wave behind it too.
Yeah. Now look at this. This is where the sun is emitting radiation outwards. Venus is in front of us, towards the sun. Here's us right here. Look at what happened here. This is crazy. This is our planet. Now, right over here, this black thing was it was some kind of asteroid or meteorite coming through here. And right from here, ejected out like a big wave, just like this, to block. This thing shot at us. It shot something at us. And we shot something back to block it. Right about here, it blocked it. But it was a shot. Now, I kept thinking about this over and over, because this goes back to 2021.
I remember this, Roger. I remember seeing this.
Yeah, and it was literally a shot. And I'm thinking, holy smokes, are they shooting at us, or how could this happen? So here's what I ended up.
A lot of folks did think that it was some kind of an energy wave or something like that. And me, when I saw it, I thought perhaps it had a different charge than we have.
Well,
a different polarity.
This is what I finally decided has to be. Well, the only explanation I can give you for it as a material scientist is that we had a strong magnetic charge on our surface, which we know we do. Lightning strikes millions of times a day, I think. Millions, because of our scrubbing through all these other particles in space. It's nothing more than, you know what a Van de Graaff generator is?
Oh yeah.
It's not. We are nothing more than a Van de Graaff generator. We're
folks to bring it down to layman's terms. If you're inside of a room and you're doing sandblasting, you always have to be grounded, because if you're not, when you finally get grounded, it will literally kill you.
You'll be charged. You're getting charged. You're getting charged up.
Yes. And what the Earth does, going through all the dust and particles in space, not including the things that we can't see, is it does the same process. It's like that sand hitting that surface. It's creating a charge, a static charge.
That's our ionosphere, and you would call that the firmament. That's the border zone around our planet that is what interferes with what we're trying to bang through. And it is a little firmer, and it is covered with ions, because that's the scrub zone. That's what's heating us. It's not, global warming isn't that we can't get rid of carbon. It's because our atmosphere is swelling from burning, yes. The carbon is not, it's the scrubbing of our atmosphere. But anyway, I came up with the conclusion that we have so many excess electrons, this thing wanted to get to them, and these wanted to get back at them, and they met in the middle. That's all I can think of. So, anyway.
That would be a repulsion, a natural repulsion.
Yeah, it's going to do that if one was pulling at the other. Now look at this. This is Venus's magnetic field. It looks like a freaking apple, man.
Well, yeah. I mean, there's your toroid and your pinch point.
Yeah, but it's like it's a double backwards, upside down thing. They don't do that. That's very, very strange. Very strange. And
amazing picture.
Yeah, some of this stuff is just out of control. And
and you know, it's interesting too that a lot of things that have been discovered, quote unquote, over the last decade have been completely independent researchers, and it's taken decades for any recognition at all, if they get any. You know, being on the fringe is actually, you know, the ironic thing about it is for a couple of centuries, the people who were on the fringe of science are the ones who were doing all the developing. And now that they have gotten themselves hardened and locked in, if you're out on the fringe, it's really difficult to even be listened to, let alone found.
You'll be destroyed. You'll be destroyed. You will be, your future is in jeopardy. If you,
well, you know, today, if you were Benjamin Franklin doing all the experiments that he did that led to where we're at today, he would be completely ignored and ostracized.
You know that this is not new. You know who Herodotus was.
Oh yeah, Herodotus. Torturous reading, but yes.
Well, yeah. Well, actually, I like his reading because he talks about things that were so unbelievable at the time, just the kind of things I'm talking about. Although I have the evidence, he came back from his trips to Sparta, and he said, look, here's what I found on my journeys. And they called him at first the father of history. Now this goes back, I forget how many BC, but at first he was called the father of history because he went through all the lands and collected all the stories, documented them, all this, and then they were so exceptional that the people that had already made up their own interpretation of history said, this guy's a nutcase, let's destroy him, and they exiled him to, I don't forget where, Malta or somewhere.
Yeah, it was.
And then he was called the father of all lies.
Oh yeah.
There is no escape. Once it is Max Planck said he said science advances one funeral at a time, and that's basically true. The guy's got to die before you can get another person to listen to you. But anyway, this is light spinning. It spins just like a drill bit. You see it?
Mm-hmm.
And that's why you get all these separation patterns. It spins over this way, sometimes it goes that way, sometimes it goes this way. Under and over, under and over. And then that's why you get, and they don't like each other. The white ones push like hell against each other. Mm-hmm. So, and here's the development of the electrons. This is where it really gets cool. Here's a green electron, photon. You see that? The green is exactly identical to the red and the blue. All right. Now, and the black particles are one size fits all. Nobody's got a bigger one or a smaller one. Now, here we're going to go.
It's interesting. It's interesting that when you show that light before with the spiral, it's the way that in the macro, it's the same way that the Birkeland currents work. They have a twist to them. So you know what's above is below.
Yeah, well, you're talking about the Higgs.
Yes.
Yeah. These are the Higgs.
That spin to them is the same thing that you see in the macro, in the grand scale of a Birkeland current. It has a spiral to it as well, and then they also spiral around each other. And I wonder if that's not the reason why we get such a nice pinch point with your laser.
Well,
that rotation.
Well, the Higgs fields are when the particles are coming back together. You see that little white? You see that little white spritz?
Yeah.
Every one of those is one of the white particles all by itself, and then all of a sudden it begins to take on the black. Now, at that point, they start to tumble. Now, let me show you a similar occurrence.
The reason why I bring that up, let me make it something a little bit smaller. Okay, we have an old-fashioned sand clock where you turn it upside down and the sand starts running through. At the top, it looks like it's just falling straight down. But if you look at the bottom of that clock, you can see it starts to spin.
Well, there is a spin to virtually everything. It's called the right-hand rule. But anyway, here's how the light comes in from the laser here is way off to the left. Now, you don't see any light whatsoever. There is particles up here where my cursor is. You don't see them at all because there's no concussion to them yet. They start to concuss up here. You start to see them show up just a little bit up here. But here, different story, because we're right in line with the Venturi. So we have to accelerate. A Venturi forces acceleration. Now, after the acceleration, you have compression, because they're stacking up their fields against each other. So now they begin to display. And at this point, you see a little glowy one over here. This is what you'd call a tau neutrino. It's not a particle, it's not a photon yet, and it's not a gluon. It's got an extra black. Then you go into the two gluons together, which I say is a photon. You see them? These are the photons. Now, you see this one has the black in the front, and this one has the black in the back.
Mm-hmm.
All right. That one has done, this is called a muon wobble. And they will always be straight up and down to Earth. Earth is the ground, but they will flip and flip and flip and flip and flip because the front particle, the white glowy part, is the one that charges up. As it charges, it flips. Then the other one, well, actually you're coming this way. So this one charges up, the white at the top. It gets real puffy, and then it flips. Hold on one second. Hold on.
You on the phone?
No, I'm on Zoom. Do you need something?
Oh, no, I'm going to see Chuck pretty soon.
Okay. All right, so anyway, it's coming through the air. This is all the same particle. And I can prove that too. We're seeing it changing flavors. That's exactly what they say. Neutrinos change flavors. That's a neutrino. These are photons. Then you get the break apart of the muon and the electron neutrino here, which is a black and a white ball. And then on the other side, they come back together as the particles again, which is the gluons, which I showed you the black and the white white is gobbling up the black. The black will end up going into the center of the white. Now, so this is the muon wobble, so that white now is in the back, and now this white is charging up. And yes, I can prove that and show that. And here
So now, Roger,
yeah.
once this goes through that pinch point where we see the flash, where the white is almost completely it is completely separated from the black.
Yeah.
The black particles that get caught in that pinch point, some of them will get through because they're the ones that are pushing. What is going on with the ones that don't get through?
They're just balling to the side. I don't know. They just get out of the way. All I can show, I'll show. We'll look at it again. But I showed you the red. The red is it separates. It's just not powerful enough to see it all in one shot. But it was all the same particle. The blue is much faster, so it's coming in hot as hell. So we know light can slow down. I showed you light speeding up before, accelerating into the Venturi. Here you can see that the two particles of the two whites do exist. Back here you would never know. It's just much too hot. So we can see light is nothing like they told us it was. Now,
yeah, that doesn't surprise anybody.
Yeah, and now let me show you the difference between the power of white and the power of red. But before we do that, here's the separation, and the blacks just go their own separate way. I don't know what to tell you, but the white is so squirty here that it won't let any blacks in. They jump in on the sides, and then they start to cuddle up here on the end, but they can't get in here. Here is just raw white. But this distance between where my cursor is here, this line up and down, and out to here is probably maybe a quarter of an inch, a half an inch. Rod is right down on top of it with the selfie. And nobody's ever seen these blacks before, except CERN and Fermilab. You will never, ever, ever see the black, ever. The only way you can see it now is because we have obscured the white from the black. It would never be this way. It would always be inside of the molecule or the atom or the proton. The black would always be the inside, and the white would always surround it, so whenever we looked at it, we'd say, well, it's just glowy particles. But no, the black's inside. They never knew it. It's been hiding in plain sight.
For all this time.
All this time. And here's where it joins back together. And I've been trying to force this down their throats, like I say, for 7 years.
Well, and folks, please note that this was done in a house with a laser, and it didn't require billions of dollars to build a collider.
Yeah, it was almost nothing. Here's my electron flood theory. Here's what it is. Remember I showed you that this is all that it consists of. The Higgs is that black and white particle together.
Mm-hmm.
All right, and the black is inside the white. We saw it, remember?
Absolutely.
All that exists is this and that. These two particles are all that exists. They can be separated, as we saw, or they can be glued together, which is the strong nuclear force. That is the strong force. They don't want to separate. They will stay together. The black is the force carrier. And it's a boson force carrier. They know this. And it pushes the gluon, the electron neutrino, because this is the muon neutrino, this is the electron neutrino. And woof, it pushes it and stays with it. It's the force carrier. The only time they separated was because of that nuclear explosion. That is just, well, it just doesn't happen naturally. You just go with that.
It requires some kind of either a concentration, like you guys did, focusing it, or a forced separation, like they use with the nuclear weapons.
Right. What they're doing is they take particles that are so dense with extra electrons that they're coated like very, very densely with those white particles. And then they explode it inwards so that everything pushes inside, and what pops is all the white particles go off first, and then the heavy particles follow.
Yeah.
Now, and it brings up a good point, which I hadn't thought about. It could be that it's not necessarily the outward force of the black, it's the pulling of the white. But how would the white pull and not have a mass to it? I don't know. It's very confusing.
Well, the interesting thing to me is when the white flash hits, there is a little bit of a compression.
Tiny.
The larger compression is when those black particles are trying to reconnect.
Right. Now, okay, so all right, think about it this way. It's one or the other. Either the black is pushing the white, or the white is pulling the black.
Yeah. Well, either way, it's the desire to come back together that's creating that force.
Right, but you got to understand, which way is it? Is it a push or is it a pull? I say now that I'm thinking about it. I got to be honest with you. I didn't really give it a whole lot of thought. I was just thinking the way you're thinking right now. Well, they just want to get back together. Yeah, but how did they get apart? And did one try to run away from the other, or did one push the other one away? Now, here's my feeling right now.
Well, under compression, one would be pushing.
Exactly. But
and that's what they've done with the nuclear weapons. They've created the compression to force one to push. But when you watch the actual footage of a nuclear explosion, you have that huge back wave. That is them trying to come back together.
Right. So the black staying there and pushing the white out and staying there and saying, "I'm gravity, you got to come back to me," or is
That's almost what it appears to be.
Or is there just an empty space there and there's nothing there? There's no black, no white.
Could be a vacuum and they're trying to fill the vacuum.
Yeah, it's hard to say because we know the black ended up coming right after the white. I don't know if it all got there or not. But
the compression wave would create a vacuum, and those particles would have to rush back in to fill in that space.
I wonder. You know what? I'm trying to think now. I wonder if at ground zero there's some kind of almost like a discharge to ground. In other words, those particles coming back to that. It's almost like a spark coming back to where it was spit from.
Yeah.
I wonder if there's. I wonder what it looks like at ground zero after the nuclear bomb goes off, right, just where the bomb was sitting above ground zero.
Mm-hmm.
I wonder
Yeah,
if
and
it is an.
because of the
I bet you there's a huge electronic discharge.
Oh yeah, you know, and we have the equipment to see that now. Back then they didn't.
Hold on a second.
We've actually got the cameras that you see in that spectrum now. See, this is the reason why we need to talk like this, folks. We need to get a lot of people together to discuss these things, because this is how science used to be done.
This is what I do all day long, man. I just do this all day long. I keep it thinking, another little thought, another little thought.
You know, somebody like me that has enough knowledge and enough experience
Here it is right here.
Seeing these things will ask a question, you know?
Look at this. Nuclear blasts trigger an effect called electromagnetic pulse, EMP. It can disrupt or even destroy electronics from miles away. That's that white blast. That's the electromagnetic pulse. Blasts miles above a country like the U.S. might severely damage electric grid and so forth. I want to know images. Let's see if there's any images of ground zero blast.
Well, yeah, if the electromagnetic pulse is running outward, that would create a vacuum behind it.
I'm interested in the electrical effects. Look at this. This is electromagnetic pulses are the last thing you need to worry about in a nuclear explosion. Well, they're interesting to me, but there's a hell of a lot of them.
Mm-hmm.
Now, what are those pulses doing? Why are we seeing magnetic? I know why. This is pushing.
It's the separation of them particles.
This is pushing so hard that the normal attraction of Earth is forcing those particles away from this area. Something's going on.
It's forcing it away from the center.
Yeah, it's always push to shove. It's always push to shove. Now, I can show in our experiments a very similar effect where the field
Well, you know, it goes back to that simple principle, Roger. For every action, there's an equal and opposite reaction.
Yeah, yeah.
I mean, you know, go back to basics. Folks, I hope you enjoy this conversation. I really do enjoy spending time talking to Roger, and if it helps people understand what he's been showing, then we have done our job right.
Yeah, well, it's good. It's good. Yeah, I suppose it's probably about time to close it up, but there's a lot of...
I am actually running out of time, too. Folks, I do homeschooling, and I am still on duty.
See this? Look at this. What is causing these stripes? What causes the crisscross smoke lines? I got some more work to do, brother.
Absolutely. And then we're going to have to talk.
These rabbit holes, they just never end, man. All right.
Well, you know, and that's the thing. I have figured out over the years that for everything that I learn, I end up finding out there's more stuff that I need to research, and that's what drives me. And obviously, that's what drives you.
No question. Look at this thing closely. Those are those push-to-shove lines. Those are the magnetic interference lines. White will always push the black away. I mean, white will always push the white away, and there will always be a black separation between the two events. That's the division line.
Yep.
All right.
You know, it makes me wonder, Roger, if at the center of the explosion, if there's not an absence of light completely.
Well, here's the center of the explosion.
Yep.
I don't know, man. There's a lot of thinking to do here.
Yep. Roger, I have got to go, but I have so much enjoyed this. I appreciate your time, and I appreciate the conversation.
I do too, Raven. Thank you so much, my friend. I'll put this up on my YouTube, and I'll send you a link.
I'll link into it.
Okay, brother.
Thank you.
All right, Merry Christmas to you. Happy holidays. Whatever you do, do it well, and have a good time. Stay safe, my friend.
Absolutely, absolutely. Thank you, Roger.
All right, brother. Take care of yourself. All right, bye-bye.